The timing of information provided in emergent conditions can be critical. Some events happen with little warning, and others are volatile and require updated recommendations around protective actions. The first step toward timely receipt of information is knowing that this information has been pushed to your smart device. When a wireless emergency alert comes to an individual's smartphone device, the phone alerts the user to the incoming emergency with a WIA cadence audible dual tone repeating signal with vibration patterns. Our previous research has shown that this alerting signal is not well noticed by people with sensory disabilities, even in controlled laboratory environments. As a result, it was necessary to study the noticeability of device signals for people with sensory impairments in their normal or uncontrolled environments. We developed a microprocessor system that allowed us to provide research participants with random signals throughout the course of the day during normal waking hours. We'd hoped for around-the-clock notifications, but our IRB frowned at that. It allows us to measure and record the time that it took the participants to acknowledge the signals, and record the status of the device through accelerometer readings to give us some context for the participant's response. For example, does the user have the device on their person? Is it being carried, or has it been left behind? Here we see one of 5 devices that we've built for the study. You can see that the device is about the size and shape of a smartphone. There's a tactile button that allows users to acknowledge signals when they notice them. Presently, the device is in an orientation mode, which allows us to demonstrate the signals the device makes to participants during an orientation to this study. During this process, we ask them for feedback about how well they think a specific signal will notify them in the event of an incoming emergency alert as they go about their activities for the day. The device signals light, sound, vibration at 3 separate strengths, and a combination of all 3 modalities for notification. At the end of the study, we complete a prompted recall interview where we ask the participants to recollect what alerts they noticed and what they think they were doing at the time they got those alerts. We compare this recall to the quantitative data taken by the device during the study. In the event of an emergency, alerting authorities at the federal, state, and local levels originate emergency messages that are sent through the Integrated Public Alert and Warning System, or Ipaws. These messages are sent through a variety of channels, including wireless and wearable devices that are accessible to the public. While these messages may look like text messages, they are not received by your smartphone in the same way, and depending on your phone's operating system, they are not accessible to screen reading software. In addition to lack of access for screen readers, these messages are not well understood by those who are deaf and rely on American Sign Language, or those who have text-based learning disabilities. Georgia Tech and industry partner DefLink developed the Wireless Emergency Alert video platform to present wireless emergency alert messages by video in multiple simultaneous formats, including American Sign Language, the Ipaws symbology, spoken English, and captions. User testing with messages have been shown to increase the understandability of the messages by our target populations. The system makes use of local resources to support operation in times of reduced wireless network capacity. This means that the system only needs to receive a trigger of a few bytes rather than to stream an entire video. Presently, the system triggers automatically from an incoming text message.
Flash flood warning in this area until 12:15 a.m. Evacuate now. Check local media. National Weather Service.
Usability testing showed that our target population wanted to be able to toggle off and on the features that would help them understand the message, removing videos if they felt that they did not need them. And so this was built into the software system. Our technology transfer partners at DefLink presented this system to FEMA Ipaws for continued development. DefLink has established a memorandum of understanding that allows them to continue development in conjunction with a joint interoperability test command, or JITC lab, so that the system triggers from an incoming WIA message.
Artemis gives us a way to test out new technologies for first responders. We enable groups such as police officers, firefighters, or EMTs to test ideas virtually without first needing to make complex and expensive physical equipment. In our current work, police officers and first responders can test out virtual displays, like the one you see here that recognizes a driver's license and displays additional information to the officer. The Artemis system lets us quickly discover pain points in implementing emerging technologies. Officers can test out ideas like this in carefully crafted, realistic simulations, finding out what does and doesn't help on the job. Artemis will also allow us to research potential FirstNet-enabled technologies to facilitate interaction with people with disabilities. For example, a police officer could use a heads-up display like this one to recognize and translate sign language.